Okay, so this week we're looking at recreating Nanite, a blog LOD generation, a blog post by uh this author who about I actually don't know their name. Xavier Neochout. Okay. Um and you find their GitHub here. So they're trying to recreate Nanite, and this is about the LOD aspect of it, which personally, how they generated LODs for Nanite was the big, how the heck could you do that and make it work? And so I'm kind of excited to see their read through this exploration of implementing it. So LOD generation taking a long time is no surprise. It's one of those things that it's not sexy. It's just rendering things in the distance with less detail, but it's critical for real world graphics to or real-time graphics to really work at scale. Um, okay. Oh, so there's another graph or another article, Traverse Research, which talks about doing the exact same things or the similar things. Okay, so the gist of the algorithm is we split the initial mesh into clusters of X triangles. So the high detail mesh, group the clusters based on connectivity, simplify each group independently, making sure to lock the borders of the group to avoid cracks, and then split the simplified group into new clusters and repeat. Um, so at the bottom level, the most reduced LOD would be, you'd probably have one cluster. And so you just repeat until you have a cluster that spans the whole thing, and then it's done. The libraries used are Mesh Optimizer, which I'm familiar with, and Metis, which I'm not, but I have to assume that's a mesh algorithm library. So, okay, so where the article uses GLTF, and previously LODs weren't a thing that was used, so there's going to be a little simple hacky LOD value added to it. Meshlets has vectors of 4 ints. Unsigned ints. Oh, is that just the size of the struct? Oh, okay. Um, okay, and then optimizing how the everything. Okay, so to get things back into UVec4 size, other changes are made. They'd make more context if it make more sense if I had read the previous articles, of which I have not. Okay, array of bytes instead of array of UVec4. Okay, and now we just gotta make sure to stride. Okay. Okay. So to load the new format, we just modify the size of the what I assume to be a vector or vector-like thing, and load it in parallel. These are the plumbing changes that get made to facilitate fun algorithmic stuff, like generation of LODs. Okay.
So can we recap? Um, I wasn't. I'm having a hard time following what. So are they essentially just chew like they just are prototyping and added a new like is that a vertex attribute or what? I'm trying to.
Uh, maybe. Um, Frankly, I kind of glossed over the GLTF specifics when I glanced over. My understanding is that they're loading a GLTF file, um, and a simple GLTF would just have a big vertex buffer and big index buffer, but I believe a meshlet style would have many smaller buffers that need to be processed, I guess, but um, I'm not exactly sure. I mean, maybe the previous articles, is there a previous, if I just, okay, the blog, okay, this is the one clustered rendering. Okay, so,
Okay. Yeah, I see there's a whole series.
uh-huh, okay. Wait, is this, oh, the plan. Okay. Visibility buffer, cluster generation. Oh, so this is the Metis library. Ooh, yeah, fancy algorithmic stuff. Yeah, when you can split a mesh into meshlets, you need to then render it.
Was
Um,
that Brian Karras's?
yeah,
Is that?
Brian Karst is like was
Oh yeah.
he at least presented the Nanite talk. Is he also the technical lead behind Nanite?
I That's my understanding.
Yeah, the link to the talk is probably here if I okay. Yeah, here's the overview. Oh, this is not the talk I was thinking about. No, that is just the documentation, which is yeah, this is what I was wanting to go for. Okay, I just want to see if he says what he is. No, he just goes straight into the technical. Okay, yeah, yeah. So yeah, yeah. Brian Karras definitely has his fingers all over Nanite, and Xavier wants to re-implement parts of it at least. Um, the LOD stuff is certainly a really cool thing. Cluster rendering, is there anything in here we need to? I think the cluster rendering, uh, you just get a list of clusters to render, and how you render it is, described in this article, but the way you get that list is kind of irrelevant for the purposes of, sorry, like this one is the one that decides those uh, LOD clusters and which ones get rendered, or it's not which one gets rendered. Actually, yeah, which ones get rendered based on the LOD distance. Whereas this one is going to be the actual rendering of those and sorting, and this is where the occlusion culling would be happening. I have a cat on me, so apologies if I whack the microphone or anything weird. Okay. Does that answer your question?
Yeah, things are a little clear. I think we can keep going and
Okay.
I'll probably pick it up.
No, yeah, feel free to stop me at any time. Um, okay, so jumping past it. So the first approach only works for connected meshes, which is there are no there are no vertices with the same position but different indices connecting them, I believe is what that is referring to. So we split it into clusters of some number of triangles. We group them based on how many neighbors they have. Um, we simplify the each cluster, each group. Oh, wait, mm, oh, okay. So we group so we have a mesh, we get clusters, we group the clusters, and then we take all of the triangles in that group and simplify that. But the borders on the group are locked so that they don't change.
So
Um,
those are going to be full resolution pretty much for all
mm,
edges that are shared amongst groups. That's how I'm understanding.
on the level, on that LOD level, yes. But okay. Actually, where was that? This is the thing that confused me. Let me find it real quick. Okay, skip past. Yes. So, okay, get bigger with a purely hierarchical LOD, you have the problem of a where is it? This where you have the boundary is locked to the top level and you get just awful performance really because you have a ton of small triangles next to a ton of huge triangles and they're, not really well divided and that's just because the hard level boundaries were decided well, in a context that really doesn't suit the size of the clusters being generated. And so Nanite gets rid of that and creates nice boundaries between LODs. And how it does that was like, first we divide up everything like this, and then we group them together, and then you draw the rest of the owl, and everything just works. And you do it again. And I'm like, wait, what?
Ooh, can you go? Yeah.
So yeah, and so the boundaries of clusters between LOD A and N and N plus 1 are the same, but N plus N and N plus 2 are not the same. The boundaries do not line up. So you can't have more than one level of boundary difference but generally you only ever have two LOD levels active at a time. But the beauty is with Nanite is that you can have LOD X and LOD X plus one rendering at the same time because the front half of the model is higher detail than the back half. And there's no seam between there's a seamless transition because everything is rock solid, no cracks. Um, the way I mean this describes it this is kind of the generalized version. You have a bunch of clusters, you group them together, you merge and simplify it, and then you split it into clusters again and you repeat. And at the end of the day, you get this DAG, directed acyclic graph. You do not get a tree. And that's the thing that Nanite that blew my mind was this tree thing, and I'm like, wait, how the heck does that even work? And so that's what this article hopefully was making a little clear about how you actually go about doing this, not just that you create a DAG out of the LODs instead of a hierarchical tree. Um,
Yeah, that's very helpful. Thanks for explaining.
yeah, I realized I, you know, looked at this for an hour or whatever over the last whatever time I've looked and thought about it. And it's just a lot of text. And I'm like, well, wait, how does that work? And then, they do a lot of discussion on uh, mesh simplification and error analysis. And it all just kind of went over my head. But um, maybe there's things you could do. Anyways, so
That's
this is this.
interesting. I heard of DAGs being used for voxels, but not for vertices.
Well, these are LOD clusters rather than vertices themselves. Um, but I was hoping the pictures here made it things a little clearer. So we have, um, since it's a more or less recursive process, n and n plus one are useful synonyms for whatever recursion level or iteration level we're currently dealing with. So we have like the top of the helmet here. We have four clusters, the green, dark green, gray, yellow. It's all one group. You simplify it together, and that you keep the boundary. Uh, you lock the boundary, so the simplification trying keeps the triangles on that boundary, or at least the vertices. Maybe it. No, it has to keep it, I think. So that way the groups next to it are perfectly aligned with it, and you don't have any holes or gaps. Mm, okay. So to find groupings of reasonable quality is not a simple thing. And Epic Games used this library, Metis, which does that for you, and there is little reason to try to do it yourself unless you also want to implement that algorithm directly. So, I mean, more power to you if you want to do that. I'm of the, oh, someone's done all that kind of fiddly graph theory implementation details. Thank you. I will gladly use it. Nice little note about using the project. So, but the logic of it is you have clusters. You create a graph of the clusters where each neighboring cluster gets an edge in the graph. So the dark green cluster here has neighbors 0, 1, 2, 4, and 5, and we, have an edge between them. And similarly, 0, 1, 1, 2, 2, 4, 4, 5 are all, well, neighbors in a row, and so they each all get edges. And then, okay. Yeah, so let's actually dive into some code. Given a list of meshlets, output a list of groups. Yeah, that's a reasonable thing to want. Meshlets. Okay, so is this just building a group with all meshlets? Trying to, oh, meshlet group.
Yeah, it seems to just build a group with all the meshlets and then put it in a vector. Oh, because it returns a vector, you see.
Okay. Figure out which meshlets are connected. Identify edges by a vertex pair A, B, where A and B are indices inside the vertex buffer and A is less than B. Okay, they share edges. The vertexes A and B, and we're using indices, so the index A and B. Oh, whoops. I need to take a moment and respond to a work thing, actually. Sorry. The cons of doing work right before a meeting is sometimes you have to revert things that are actually broken.
That's always fun.
Yeah. I'm trying to think of the thing. Okay. Okay, and create pull request. Okay. I clicked the revert button. That is good. Okay. Sorry about that. Okay, so identify edges. Iterate over all edges of all meshlets, recording their edges each time. How are we finding the edge of a meshlet?
It's actually never mind. I thought I had an idea.
How are the meshlets stored? Like, what's their data look like?
That's a good question. Is this Nanite the plan? Cluster rendering. Meshlet data, vertex offset, vertex count, index offset, and index count. Okay. Meshlet vertex indices, list of U32s. Wait, how do these differ?
One is probably the indices of meshlets themselves.
Oh yeah. You gotta ax okay, if you have a vector of meshlets, you really have a vector of vertex buffers of a small size. And so you can index into the first, list and get the meshlet, and then you have to index into it to get the actual vertex. Okay, that is where I was being confused. Cluster. Um, okay, I guess, I mean, in one sense, a cluster is just a fancy vertex buffer. Or a meshlet is just a fancy vertex buffer, but it's not in the API that we're saying there is a separate buffer. It's a pure semantic description on top of a flat array of data, usually. Okay, I'm getting distracted by trying to read another article quickly and getting nowhere fast.
But I guess the answer is they have a index buffer, so you can just look at adjacent indices in there to get edges.
I think so.
Makes sense.
Okay, the code moving around is annoying as I move my mouse.
If you look in the chat, I put a little thing you can paste in the console that will expand
Oh,
all of them and keep them expanded.
no,
Which
don't
shot did you put this
delete
on?
it, copy it. Oh, I almost deleted the message. F11? Nope, F12. Where's the silly console?
Oh yeah, you have to type in allow pasting and press enter before you can paste.
There, thank you. Thank you very much. That makes this infinitely more lookable. Okay. And we don't care which vertices are the boundary. We just care what meshlet indices, which index into the meshlet array it was. Um, hmm. Okay. Get vertex index, primitive, meshlet vertex indices, index into it based on the Meshlet indices based on it's you have an index, you have the men index offset, then you index into Meshlet indices using that, and you offset on the vertex offset, and then you okay. So from the other article, yeah, Meshlet vertex indices and Meshlet indices are the big vectors that contain everything, whereas the Meshlets are just a. Oh, okay. I was missing that bit of detail that a meshlet, as described here, it is just a description of where in the vertex buffer and index buffer this meshlet refers to. Okay.
That makes sense. I was missing that as well.
Yeah, a meshlet does not contain the data, it contains
Just
pointers
offsets.
into the data.
Yeah.
Okay. That is
Yeah,
good.
there was like a diagram in the other article as well, like with the pointers.
Oh, yes. Oh, that's the plan. This, yeah, this thing that I
Yeah,
kind of
that
just
thing,
scrolled
yeah.
past.
Yep.
I assumed that this was a vertex compaction, that okay, I am reasonably confident that there is a. No, I have to go back further. No, it's okay. It's further along than that, apparently. No, don't reload the whole thing. Okay, there is. When you render stuff with 2-pass, this is kind of what I was thinking. That this was a diagram that it was referring to, where you have this is a 2-pass occlusion culling, where you yeah, I don't need to explain this. I thought that this diagram was referring to like prefix parallel sum reduction and filling in the data from the result of the compute shader. I'm off my rocker apparently tonight.
It does look very familiar.
Yes. Maybe it was actually. I want to say it was the visibility buffer rendering. I want to say it was this article series that has a very, yeah, this, doing this whole compaction and material sorting and indirection stuff. That's what I thought was being referred to. Wow, I just spent like 3 minutes trying to explain a random idle thought. I'm sorry. So we can find the edges in the graph using this algorithm presented here, where there's lots of indexing into the big vertex buffer based on the meshlet, and subdividing everything up from that, and iteratively go through all meshlets and find all neighbors. For each triangle, for each edge of the triangle, find a... Oh, that's why they're using an unordered map, because if you find the index, you can find all its neighbors from that. I'm guessing based on what I'm seeing. And then, clear out any degenerate edges. And then, okay, the Metis library has to work on adjacency, compressed storage format, a list of edges, and then xadj, range of indices inside the adjacency. My mind is saying half edge structure for this description, but someone please correct me if I'm wrong.
My understanding of half edge is it's useful for like manipulation of meshes. I'm not sure if it's useful in the context here.
Hmm. Okay, it seems to be a lot of work to just take the Meshlet data as we have created it above and then turning it into a format that Metis likes, which is this format where we have a list of edges and then the vertices are organized. I'm trying to parse what this is saying. I wonder if the Metis library has clear documentation than that sentence there. But I think to get to that, we'd have to parse their documentation that isn't trying to only explain that.
I heard that this library does not have amazing documentation, and that's actually, in fact, really confusing. So it might
Oh,
not be that helpful for us.
okay. I'll ignore it. Or I will leave this open, but I will not try to parse the source code for that information. Because if there's no documentation, then source code's the documentation. Okay. Oh boy, that's a fun disclaimer. And you get groups back from calling the function. Okay, so we've grouped our meshlets. Just need to merge and simplify them. So concatenate index buffers. I mean, that's as simple as just, you know, writing, yeah, creating a new
I'm copying them.
array and writing the indices in. Oh. And then we have a big meshlet, combined one, which we need to simplify, of which we use the article uses mesh optimizer. Just divide the triangle number in half is what we want to do, and make sure that the borders are locked. Um, uh, okay. So then now we have a new meshlet index buffer whose indices are for that buffer, or for the new vertices generated by the simplification process. Okay. Well, the nice thing about this algorithm is the first LOD is the same process. Okay. Wow, big wall of code setting everything up.
I didn't realize that the mesh optimizer library does so much with meshlets.
Well, there's a pretty great explanation for it. Is there, where's mesh optimizer? Arseny, he was like, hey, NVIDIA just unveiled all their mesh rendering stuff. I want to play with it. I'm going to add a bunch of the supporting infrastructure to my already existing mesh optimizer library, and just made all that work easily accessible. And it does all this stuff because he wanted to play with it and wrote all the necessary, building blocks into the library so you don't have to, and it is great. Like simplification. I mean, Mesh Optimizer itself is if you wanted to generate more traditional LODs where you have like a high detail, like you have 8 or 10 LOD levels, and you just generate a separate mesh for each LOD level rather than this fancy clustered approach that we're talking about. And so doing it on a meshlet is just a simplification at a different scale. A couple of hundred triangles instead of 10,000. Yeah, see, mesh shading kind of spurred on all this work, which is awesome. Okay, we're merging everything together. So clustering meshlets from the index buffer. And yeah, mesh optimizer has a meshlet thingy because it just does. And so LOD n+1 is generated from LOD n, which, because it's a recursive or it's iterative, recursive, whatever, instead of using the original LOD, the original model for every LOD level, there is the possibility of error creeping in over time from like not just floating point error, but just you simplify the model and then you're simplifying a simplified model. You're not trying to simplify the highest level detail one down to, a quarter or an eighth resolution. And instead it's doing a half resolution each level. So I believe there's more discussion about error metrics later on because of that. Okay. Yeah. Generate. Ooh. And we group, if we've generated the meshlets, we group them, we simplify the the groups, which this seems to be a lot of the above pulled into one function. And then ooh. Okay, yeah, this is the error I'm discussing. Yeah, the lovely thing about very low fidelity LODs is they do not need to look good if they are going to be a couple of pixels on the screen. In fact, you don't want a lot of triangles. You want a low number of triangles for that.
So
And
is this error using like a screen space error type of?
I think it's using no, I don't know actually. Does the
So I know
is it
like 3D tiles specification, which is also an LOD type of approach, has pretty good documentation on how the screen space error is calculated.
okay, I think I'm rocking what you're saying, and I would have to reread this paragraph to be able to really.
Yes, essentially, like if you simplify and say that this mesh can be no more than, like I do this with terrain where it's like the simplified mesh can't be more than 30 meters from the original mesh. Like no vertex can be 30 meters far, like away from the original source mesh. And so if you know that error metric is 30 meters, then there's a screen space error metric that you can, based on how far the camera is away from that geometry, you can say, all right, well, 30 meters fits within a pixel, so I can use that level of detail. That's essentially.
Yeah. Okay. It
Yeah.
might be. I would need to. What this article is using as an error metric and what the Nanite is using as an error metric might be slightly different. They might be identical. Assume most clusters draw at constant screen size. I mean, like that. This is, big chunk of text. Okay, and so this is showing the different LODs from the most detailed to the least detailed using a Stanford bunny. And you can see there's no more, there's only 7 levels because there's just not that many triangles to begin with. And it does a pretty aggressive clustering and simplification on each step. Yeah, when you have fully connected meshes. Oh, does it just mean like meshes which are just made out of a bunch of patches rather than a continuous, closed object. What is it? There's a specific name for
Manifold.
that's not the word I was looking for, but probably the right
Or
word.
yeah, but essentially the edges, like if you have an edge that's like if you have like you can't have two adjacent triangles that don't actually share an edge in the mesh, according to this.
Yes, you are correct. What I was thinking of is not actually relevant here because I'm thinking of a um like a mesh with a inside and out it defined inside and outside, which isn't really relevant for what we're doing here. Uh what is it? It's go whatever. Stop thinking about it. Okay, yeah. That's actually kind of a problem if the vertices that are in the same position are distinct because they're like using separate concave mesh. Thank you. That is the word I was looking for. It needs to be like a convex hole. Thank you. You reminded me of the words I needed to look. Uh, yeah, see, it's not relevant to what we're discussing here. Whether there's an inside or outside is like, we don't really care about that. We care about whether the edges are all connected together. So, yes. So from the documentation of Mesh Optimizer, you got to weld the things together. From my experience of creating 3D models, it was sometimes very useful to have different vertices at the same position so that they could have like different UV coordinates, which is annoying if you're trying to weld everything together and maintain UV coordinates for your mesh. Uh, okay. You got to find close vertices if you want to merge them. Mm. See, okay, yeah. Um, yeah. If the UV coordinates are different, then you're gonna have a bad time when you try to merge them together and find out the wrong UV coordinates are being sampled and it looks all funky. How do you get around that? Everywhere a vertex is accessed by its index. Oh. So that's just working around that limitation of Mesh Optimizer, it seems. I mean, you can solve every problem in computer science with another level of indirection. Okay, so to better merge vertices, don't just blindly iterate over all vertices in a triangle fashion. Find the neighboring vertices that are less than a distance away without having to look through all of them. Binary space partition. Okay, and we don't even go over it in detail because it's already a very long article. Ooh, KD tree per LOD. Okay. Okay, and this is the faceted model with lots of subparts that don't really connect to each other. That is wacky. So we reduce it to 10%. Ooh, that looks, wait. Yeah, that looks way better. It's still not a closed surface, but it's not as wacky as the triangles here, which just kind of feel like they're degenerates. Mm, yeah, look. The neighbors are completely different, but the location is right next to each other. The location in the, sorry, the 3D space location is next to each other, but the 2D space is very far apart. Ugh. Okay. Uh, yeah, just automating the process is an improvement, making it do a little bit better quality, making it faster. I mean, those are all three things now. I'm not going to go and try to read the next article, which seems to be more details, but I appreciated this article's uh, in-depth code context because when I read this description of, how they do something, you can get a lot of ideas about how it works, but it's nice to be, confronted with an actual implementation where you have, where was that? Wasn't here. It was this guy, where it was like indexing an index to index into the next index using offsets of, three different things altogether. Um, it's nice to get a bit of reality check on exactly how deep the rabbit hole is going and a couple of words being described to describe the actual the couple of words that are used to describe the algorithm result in this funky, you know, indexing scheme that, you know, when described in simple English hides all the complexity underneath. So, okay, that's satiated my curiosity. Um, I'm still trying to get a better like grasp of the um way the LODs work and how you can have LODs of different levels. But I suppose the crux is that you can only have differing LODs of one level or the same level. You can't have vastly different ones because you effectively create a whole new mesh for every LOD level you generate. You don't have common boundaries. You don't have seams along the edge. You just, can I pause? I cannot pause that because it's a GIF. Darn.
But see, like in this GIF, we're going through, like there's no, like we're looking at all of LOD 5, all of LOD 6 in this. So it's not quite showing how LOD 1 looks next to
Well,
LOD 2.
look at the okay, not here. LOD 1 and 0. there was an edge with a dimple downwards. Yeah, here. Oh. And do you see how it carries between the two transitions?
Yeah, okay.
And so that would be where you could cut it in half and get, one higher and one lower LOD level. And of course I had to click it. And so I'm seeing a couple of those places where the edges are shared. Of course, at like LOD 7 or 8, it kind of, you have one level, so it doesn't really matter. But once you jump up to 2, you could have, I guess it'd have to, well, sorry. When I say 2, I really meant the least detailed version. When you have the least detailed version, you have just one cluster. And then when you have the second least detailed, you have a couple of clusters. And then when you have the third least detailed, you could also have the second least detailed on one half of it because their borders will be kind of shared. It's a bit fun to watch to look where the borders stay constant. Although it'd be easier to see
So,
that if there was like a wireframe
yeah,
outline.
one thing I think I'm trying to pick up on is if they force like an overlap between meshlets of different LODs as a way to avoid cracking.
That is my understanding. I mean,
Although if you did that, then wouldn't you have some weird Z fighting when, like, if you have like one LOD that's kind of
well,
has triangles?
you shouldn't because the like this border here would be the one used between this level and this level, if that
Okay. Yep.
makes sense.
It,
So
that does, yeah.
so if we wanted to, I mean, I really wish I'm just mentally copying the image and moving it slightly over, and then the borders here would be this is the border that this group came out of, and the actual triangles or the lowest level of detail, the triangles are going to be much more detailed here, but this was the group of the previous level that was clustered and split into clusters that could be then rendered in a clustered fashion. Um, uh, yeah, see, like you can't do an LOD, that you can't draw a line between the well, yeah, you can't draw that line because it's crossing the edges.
Oh, can you go back up to that the just a little bit more? That right. So if we are rendering LOD 0, the yellow and red, but then the purple is rendered because it's a little bit further from the camera.
mhm.
Purple contains the geometry or the edges for red, green, and is that cyan? No, I don't know, light blue. Am I understanding that correctly? And so the overlap would just actually be sharing the same geometry in that case. I don't know. There's something there.
I'm also trying to conceptualize it because I'm like, yeah, the purple here has edges with red and yellow, and if we look at this graph here, we have these two clusters, the red and yellow, and then so like the neighbors are constant, so the clusters all around here would have the same edge, and you could swap out these 4 clusters with these 2 clusters. Um, and so I think the annoying part about this graph is to make it clear, there's only one instance of this, DAG going on, but the actual where was it? The actual thing would be like, this top level blue one has a whole bunch of green ones, and then each green one has a whole bunch of red ones. And so, and I think each of these Voronoi cells, each of these cells are contain a certain number of clusters themselves. They are not a cluster on its own. And I think that's a confusing part about trying to read this presentation for me. Okay, I'm gonna zoom out just so I can read the text a bit better. So the group boundaries, and hence the edges that will be locked during simplification, alternate group boundaries from level to level by grouping different clusters. Now at level 1, and then we just, what is it? Boundary 1 becomes interior of the next level. Yeah. Okay. Okay, there's just a whole lot of anecdotes about different things that are not inevitably relevant. What are tetra puzzles? Oh boy. I forgot all about that term. Okay. So is this just I'm trying to okay, I'm getting to the point where I'm randomly looking at information and I'm not really coming to any sort of conclusion based on it.
Yeah,
And so I think we should
let's stop recording.
yeah.